For decades, our digital world has been built on the elegant simplicity of bits, electrical pulses representing either a 0 or a 1. These classical bits power everything from our smartphones to supercomputers, performing billions of operations per second. Yet, even with their incredible speed, there are problems that remain stubbornly out of reach. Simulating complex molecules, optimizing vast logistics networks, or breaking advanced encryption often demands computational power that would take our fastest machines eons to achieve. This is where the universe itself offers a new paradigm, the realm of quantum mechanics. At the heart of quantum computing lies the qubit, or quantum bit. Unlike its classical counterpart, a qubit isn't limited to a definitive 0 or 1. Instead, it can exist in a superposition of both states simultaneously. Think of it not as a coin showing heads or tails, but as a coin spinning in the air, embodying both possibilities until it lands. This ability to represent and process information in fundamentally new ways is the cornerstone of quantum computers. Physically, qubits can be realized in various forms, from the spin of an electron to the energy levels of a superconducting circuit, each carefully controlled and isolated. Superposition is perhaps the most mind-bending property of qubits. If a classical computer needs to check every possible path in a maze, it checks them one by one. A quantum computer, through superposition, can theoretically explore all paths simultaneously. This doesn't mean it tries every path at once in the classical sense, but rather that its computational state holds information about all paths in parallel. It's a probabilistic landscape where multiple realities coexist until measured. This exponential increase in information density allows a system of just a few hundred qubits to store more data than there are atoms in the observable universe. Beyond superposition, there's entanglement, a phenomenon Einstein famously called spooky action at a distance. When qubits become entangled, they become inextricably linked, sharing a common quantum state. The measurement of one entangled qubit instantaneously influences the state of another, no matter how far apart they are. This connection allows for highly correlated information processing. Imagine flipping two coins far apart. If they are entangled, knowing the outcome of one immediately tells you the outcome of the other, even before observing it. Entanglement enables qubits to work together on a problem in ways impossible for classical bits. Just as classical computers use logic gates, like AND, or NOT, to manipulate bits, quantum computers use quantum gates to manipulate qubits. These gates perform operations that can change the superposition of a qubit or entangle multiple qubits. Unlike classical gates which produce a definite output, quantum gates transform probabilities. By applying a sequence of these gates, quantum algorithms are constructed to harness superposition and entanglement to solve specific problems. The challenge lies in precisely controlling these quantum states, maintaining their coherence while performing complex operations without disturbing them prematurely. Building a functional quantum computer is an immense engineering challenge, primarily due to decoherence. Quantum states are incredibly fragile. Even the slightest interaction with the environment, a stray photon, a tiny vibration, a fluctuation in temperature, can cause the delicate superposition or entanglement to collapse, forcing the qubit into a definite classical state. This loss of quantum information is decoherence, and it's the enemy of quantum computation. To combat this, qubits are typically isolated in extreme environments, chilled to near absolute zero in cryogenic refrigerators, or suspended in ultra-high vacuums to minimize interference. Despite the hurdles, significant progress is being made in constructing these extraordinary machines. Today's quantum computers come in various forms, each with its own advantages and challenges. Superconducting qubits, often seen in IBM and Google's processors, leverage superconducting circuits cooled to millikelvin temperatures. Trapped ion systems use precisely controlled lasers to hold and manipulate individual ions. Photonic quantum computers use light particles to carry quantum information. While these systems are still relatively small and prone to errors, operating in what's known as the noisy intermediate-scale quantum or NASQ era, their capabilities are steadily growing. The true promise of quantum computing lies in its ability to run algorithms that are intractable for classical machines. Shor's algorithm, for example, could efficiently factor large numbers, posing a potential threat to current encryption methods, while Grover's algorithm offers a quadratic speedup for searching unsorted databases. Beyond these theoretical breakthroughs, quantum computers are poised to revolutionize fields like drug discovery, enabling simulations of molecular interactions far too complex for traditional methods. They could also accelerate the development of new materials with unprecedented properties, or optimize logistics and financial models with remarkable efficiency. We stand at the cusp of a new computational era. While universal, fault-tolerant quantum computers are still some years away, the progress being made is astounding. Every day, researchers are pushing the boundaries of what's possible, refining qubit stability, improving error correction, and developing more sophisticated algorithms. Quantum computing isn't just an incremental improvement, it's a paradigm shift that could unlock solutions to some of humanity's most pressing challenges. From medicine to climate science, the ability to model the universe at its most fundamental level promises to transform our world in ways we are only just beginning to imagine.